Okay. Screen share is loading. Screen share is there, I think. Okay. So I will need to cut the recording at the end because I muted myself by accident. Sorry about that. So we're going back to the Wikipedia page. And I just wanted to explain. I just wanted to explain the depolarizing channel. So depolarizing channel. This depolarizing channel means you take a matrix A and then you divide one by the dimension, which is a number, and then you take the matrix, take Z, A, Z, plus Y, Z, no, Y, A, Y, plus X, Y, X. Okay? And I want to explain that this is basically averaging over with Schur's lemma. But there was this problem that I was explaining just before, that if I take Z, X, Z, then I get minus X, this we knew. But if I take two elements Z, X, I get IY. And there's additionally, this additional group of identity I to power 2, I to power 3, which is minus the minus I, and I to power 4 will be identity again. So there's this multiplicative group here. Okay, so you can keep multiplying them and on it goes. So there's additionally those factors here. Okay. And I could, in principle, imagine taking a big group like here, plus minus I to power mu, where mu is 0, 1. And here I have identity Z, X, and Y. I was writing it carefully before, right? But this is many elements. So maybe that's annoying, okay? And if I'm not completely mistaken, there's something called the center of group G, which is denoted by Z of G, because in German center you will write with Z. And there's something called quotient of G modulo some subgroup H, so you would write G over H. And so if I consider G sub Z of G, that will give me a new group. And if I'm not completely mistaken, I wanted to say that this G prime prime, if I would consider here, that wouldn't have the phases anymore. So that would be a different group where you quotient out those phases. Okay. So the center would maybe be considered by making the adjoint of all the diagonal elements or something like this. And the diagonal elements allow me to factor out all this stuff, which means I can single out the non-trivial matrices, identities X, Y, Z, X, Y, and those are those 4 elements here. So if I'm not completely mistaken, luckily it's a tutorial, I always escape into saying that. I think you can view the depolarizing channel as Schur's lemma averaging over a group where you use this quotient construction modulo the center of the group. So if you're using, if you study undergraduate group theory in mathematics, I only read once some textbook a bit, and so I don't remember it carefully. But back then I wasn't so sure about those quotients and centers. It was quite abstract. And that's a very nice application, I think. Okay.
So for this to hold, you need the reducibility of the representation, right? So is it guaranteed that the quotient group is also reducible if the representation of the quotient group is also reducible?
Yeah. So you will need to be checking all those things. So yeah, I'm not prepared to answer all those questions, but maybe we improvise a little bit and hop around Wikipedia a little bit, yeah? So irreducible representations. Let me see. Okay, I saw it there, irreducible representation. So I will open irreducible representation. And let's check whether if I go with Z2 into those general linear matrices, then basically maybe there's some symmetry sectors, okay? So there's maybe some subgroup which behaves like an identity. So for example, yeah, so basically the fact that Z stays invariant under Z, it's already hinting that there's maybe some symmetries that are still left over. When you have symmetries left over, that would be reducible representations. So just to tell you what I'm thinking about, when I had one and identity and Z matrix, if I applied Schur's lemma, so I got Z plus Z, 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 1/2, gives me again Z, which is not proportional to the identity. The first thing that why it's not becoming identity is maybe because it's not an irreducible representation, okay? And now what Jongrak is asking is that if I consider this group G's modulo the center ZG, to see that the depolarizing channel works, maybe we need to ask whether this is an irreducible representation, okay? So maybe there's a little bit more work to be done, but I'm not really prepared to prove to you all those relations here, okay? So the next thing we will do is we will look at the depolarizing channel. Quantum depolarizing channel. And let's see if I can find center. There's no center here. And group. Also no group. And Schur, also not group. So why does 12 of quantum channel give a depolarizing channel? So let's check on Stack Exchange. Yeah, so here will be some more answers. I'm just browsing through. Okay, reducible representation, right? What's this? Yeah. So you can read more here. I think those will be very good answers. Markus answered here. So this will be a very good answer. Markus Heinrich. This with the center, I was learning from Markus's thesis. PDF maybe we can find. Okay, maybe on his webpage it will be there. Publications, exactly. That's the PhD thesis. Okay. So you can find it on Markus's page, the link. And then this is the Cologne University webpage. And you will find the polarizing. Yeah, he doesn't describe it here, but twirling will be there. Huh? Twirl. Clifford twirl. Okay, twirling operation, group projection, and so on. Yeah, so this is a very mathematical thesis, and I was trying to read it, but yeah, but then it gets quite mathematical, and he answered here to explain this with the irreps, I think. Yeah, so yeah, you can write this as an integral, but you can also write it as a sum. So maybe that's explained somewhere here or something. So yeah, okay, maybe some more googling and maybe you can find more information. Usually there should be pretty good stuff. If not in this thesis, then in the references. Yeah. Where are the references? So in some of those references, there might be, I guess, the thesis by Gottesman that started error correction would be helpful. And that's a paper, but there's a thesis by Gottesman. Maybe stuff like the stereo fault tolerant quantum computation. Maybe there you will find the correct formulas. Maybe actually in this. So on the archive 9705052. Maybe here we will find depolarizing channel. Yeah, here we have the depolarizing channel, which is suppose some probability, maybe no. Capacity is a different thing. Yeah, no, I don't know a good reference how to link those two. I was learning this from Markus's thesis about the center because he's really explaining how to remove the correct center and what's the full center of the Clifford group. The Clifford group is a bit more complicated than the Pauli group and so on. But this modulo, this center, I think this is related to that. Yeah. And here you see in some way, this is like Schur's lemma, for example. Yeah. And that does really advanced things where people really know group theory on a very advanced level, and they use it a lot. Yeah. For the depolarizing channel, I think maybe we should ask on Stack Exchange how to write the depolarizing channel using Schur's lemma. What's the group? What's the group that gives rise to? What's the group that gives rise to? What's the group that gives rise to the depolarizing channel using Schur's lemma? Yeah, and my idea was to have an equivalence class where if I take Q from 1 I squared I to power 3, then Qx is all equivalent to some other matrix because I forget the phase. So I have an equivalence class, and you could consider this as being some group as well, which means then x and x times z is whatever phase I. So let's say I work with a representative Q and representative RZ. Then I have QRXZ, which gives me some P times Y with some P, because Q and R are actually in a group. Then this is again here, which means that this gives rise to some Y, and those multiplications work out that way.
So the Wikipedia says Pauli group is a central protocol cyclic group 4 and dihedral group of order 8. So maybe it's like
okay, so I should Google Pauli group.
Yeah, so maybe like the default group is the group you want to find?
Yeah, maybe that's some nomenclature here. So you're saying this?
Yeah, like below they say as an abstract group, G1 is isomorphic to default central product default. Yeah.
Of the cyclic group of order 4, which is cyclic I to powers, you keep taking
Yeah,
powers
that's
of
the
I.
default. Yeah.
And actually they are referencing Nielsen Schwank, but I don't remember. Maybe I didn't read that carefully because I'm always working with just matrices, right? So, but you see abstract group being kind of singled out here as opposed to representations. Okay, but then if we consider this abstract group G and C4, C4 is then what we want? No, G1 we want, yeah. And then we do Schur's lemma on this, then we don't need to ask on Stack Exchange, and it's all identified in some way. Yeah.
No, G1 is the original one you like had.
G1
right?
is the original one, and C4 is more closer to the Clifford group on a single qubit. Yeah. Is that correct?
C4
So
is just like C4
no,
is
but
just 1i minus 1 minus I. Right?
yeah, and then the dihedral group is
So yeah,
because
D4 is
maybe we
like
don't need the central product, right? Maybe we can take one of those, and then this will give us the depolarizing channel. I was thinking.
yeah, D4 has representation with like identity minus identity, X minus X, and some anti-symmetric parts,
Yeah.
and Z minus Z.
Because the antisymmetric parts we can take, right?
So yeah, if we like
Yes,
remove
yeah.
the imaginary part of the Y operator,
Because I can take this minus Z, but this is equals to 2 times Z AZ, yeah? So if I forget the i's, this will be fine. Well, anyway, the way it goes, that at some point you get to ask somebody who knows, and you, now after this tutorial, you know what to think about and what to search for. Okay, let's finish here. Or Jongrak, do you have a full solution to say depolarizing channel and what is the group that gives rise to it?
No, I think like default you can do the same thing with G1, yeah, without the imaginary part. But I mean, at the end of the day, it's the same map because you know the coefficients don't matter that much.
Yeah.
Yeah.
But I think I'm not wrong to say that it's not an accident that the depolarizing channel looks like that. And I think this is linked to the Schur's lemma. And I think maybe I will get to meet Markus Heinrich actually in 2 weeks. So if he will be there on the workshop, I will actually ask him. Maybe I will record the video.
yeah, I think even with the Pauli group, as I mentioned, it should give the depolarization.
Oh, with the full group without the center, you can directly go. I mean, you can always apply this averaging. And the last thing I wanted to say is that when you consider this, you constructed something invariant under the group. So if you will actually multiply another element, this H0 is invariant under adjoints. So
yeah, but I wanted to find, let's say, like the minimal group that can give rise to this depolarizing channel. And
yes, you want to find minimal group, and that's exactly why I started talking about the center, because Markus is actually discussing this somewhere here.
Yeah, and I think it is default. So
But somewhere here he's discussing the center of the Heisenberg group and the Clifford group and so on. Yeah. And that becomes quite relevant for randomized benchmarking and so on. So the Clifford group is this, Z4 and so on. And Z4 we saw. So we were kind of reproducing it. So formula 411 on page 13, Markus's thesis. Good.
yeah. Anyway, sorry for taking too much time.
No. This is a good discussion. I mean, it's exactly the point of the tutorial. So thanks for helping me out. I'm also getting lost with it. Okay. So let's finish here, maybe. Yeah.
Yeah. Like everyone left.
Yeah. Well, it was 1.5 hours today, so it was a longer session, but it was more improvised, so fine. Okay, thank you, John. Thanks everybody else who was joining, or if there's some questions, it's more or less on purpose, more gives opportunity to search for some stuff. Okay, I will upload this on YouTube and then we can discuss some more. Okay, thank you. Bye-bye.